Hello and welcome to today's video. Today's video is for Advanced Geometry, Chapter 12, Section 1, Tangent Lines. So we start out with a definition, tangent to a circle. It is a line in the plane of the circle that intersects the circle in exactly one point. And the point where they intersect is called the point of tangency. So if I draw a circle and I put a point on it, if I draw a line that goes through that point but also intersects the circle in another point, then it's not called tangent. But if I draw a line that intersects that point but only intersects the circle at that point, then he would be called tangent. So this would be a tangent. And the first thing we have is called the circle tangency theorem. This one says, if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So in this case, AB is perpendicular to OP. Now the biggest mistake I see with this one is students will see, like, I could draw a line that goes from P and goes to another point on the circle. Those would not necessarily be perpendicular. What's perpendicular is a line drawn from that point to the center of the circle. That is what is perpendicular. So the example we have here, they want us to find x. So I'm going to use quadrilaterals. So what I can say is, well, if LM and NM are perpendicular, or sorry, they're perpendicular because they're tangents, then these are going to be right angles. So if I take the 360 degrees for a quadrilateral, I can get rid of 180 degrees for the right angles. And then I can get rid of that 117, which means the only thing that's left is the 63 degrees, which has to be x. I'm going to do a justification for the circle tangency theorem, so if you want to put this in your packet somewhere where you have space, you can do the drawing for it. So assume that AB is tangent to circle O with a point of tangency P. And what I'm going to do is justify that OP is perpendicular to AB. And this is going to be, you're going to use an indirect part. Okay, so I'll do that in class. The next example is a problem that some students seem to have a hard time with. Be careful about where what you think of where the right angles are and stuff. So I have a dirt bike chain. If it's tightly around two gears, the chain and gears form the figure at the one on the right. Find the distance between the center of the gears. So I want to find this distance. Okay. So what I have is basically a trapezoid. And what I'm going to do is I'm going to draw a line that goes from the smaller radius center, and I'm going to have it go perpendicularly to the other radius. And what I've created is a rectangle and a right triangle. So if this is 26.5 for the one side of the rectangle, then this is also going to be 26.5. And I can also figure out this part of the radius, because if this part down here is 2.4, then this part right here is 2.4. So if I take 9.3 and I subtract the 2.4, I get 6.9. And so this part has to be 6.9. So now what I can do is I can set up, and I think what causes issues with this one is the fact that that right triangle is upside down, so be careful. I can say that if I take the 26.5 squared plus the 6.9 squared, that has to be the hypotenuse squared. So C is going to be the square root of 26.5 squared plus 6.9 squared. And then I'm just going to put that in my calculator because I can have a rounded answer. So 26.5 squared plus 6.9 squared, and I get about 27.4 inches. Okay. The theorem does have a converse, so we have the converse of the circle tangency theorem. This one says, if a line in a plane of a circle is perpendicular to the radius at its endpoint on the circle, then the line is tangent to the circle. So for the example they wanted us to prove that that's tangent. And the way we can do it is to say, well, if this ML is tangent, then this would have to be a right angle, which means that it would have to be a right triangle. So I'm going to use the converse of the Pythagorean theorem. So I'm going to say, well, is it true that 7 squared plus 24 squared equals 25 squared? So this would be 49 plus 576. Does that equal 625? And 625 equals 625. And so check, it does. So this angle would have to be right, which means these two lines would have to be perpendicular, which means it would have to be a tangent by the converse of the circle tangency theorem. We've been using these, so these are not new, but we have two definitions, inscribed in and circumscribed about. Inscribed in is a figure drawn within another figure in such a way that they are sharing the maximum number of points. Circumscribed about is when a figure is drawn about another figure in such a way that they are sharing the maximum number of points. So what they mean by maximum number of points is if I draw an equilateral triangle and then I only have something like that, this would not be considered inscribed in because a triangle can have a maximum of 3 points that it's touching the circle. So we would not call this inscribed in. The next one we like to call the snow cone theorem because if you take a look at the picture, it kind of looks like a snow cone. This one says the two segments tangent to a circle from a point outside the circle are congruent. So if I have a point B and then I draw the two tangents that go from B to the circle, those two tangents are going to be congruent. So AB is going to be congruent to CD, or sorry, CB. So we have a picture. The diagram represents a chain drive system on a bicycle. Give a convincing argument that BC is equal to GF. So you might say, well, why is this one called a snow cone if I really don't see a snow cone in this one? Why are we going to use it? Here's what you can do. You can extend these lines. And what I end up getting is two snow cones. So I can call this X, and maybe I'll call this Y, and I'll call this U, and I'll call this V. Well, there's two things I know. I know that X equals Y because of the snow cone theorem for the smaller circle. And I also know that X plus U equals Y plus V because it's the snow cone for the larger circle. So I can use the snow cone here too. And then what I can do is I can subtract equal things. So that must be that U equals V. And if you take a look, U is BC and V is GF, so it works. So for this one, circle O is inscribed in triangle ABC. Find the perimeter. So inscribed in means that it's touching the maximum amount of places it can, but it's fully within, which means these are all going to be tangent points. So what I can use is a bunch of snow cones. I've got this snow cone up here from A, so this is going to be 10. I have the snow cone from B, so this is going to be 15. And I have the snow cone from C, which means this is going to be A. So if I put them all together, I've got a side that's 25, I have another side that's 23, and I have a last side that's 18. So 6, and I get 66 centimeters. Done. Okay. I am also going to prove this theorem, the snow cone theorem. So given circle O with tangents AB and BC, I'm going to prove that AB is congruent to BC, and I'll do this proof in class too. So if you can take both of those proofs that I'll do and just either do them on a separate sheet of paper or put them somewhere in your notes, make sure you remind me if I forget. And that is it for today's notes. Thank you for watching.